Okay. Okay, so our topic today is the exponential function, differentiation and integration. Okay, so the question that was posed was, what do you know about the natural exponential, e? And what many of you said was you remembered that e is approximately equal to 2.718. And then I asked you, well, how did you come up with that? Where did it come from? And we forgot. So then I gave you an expression, which was 1 plus 1 over x raised to the x power. And we were told to evaluate that for x equals 10, 100, 1,000, and I'll just go down to, did I do 1 million? Okay, so for x equals 10, what is this expression? 2.704? Did it go on past that, or did it stop? Oh, we have to reset your calculator. For x equals 100, what'd you get? Wait a minute, 2.7, 2.71? You got 2.7? 0481. Okay, how about 1,000? Okay, so 2.71. Okay, and how about when x was 1,000,000? So 2.718, 28, and then it's going to go on. Okay. Now, when x is equal to 1,000,000, that number, the 2.71828, should look very familiar to you. That is the approximate value for the natural exponent, e. So here, e is the limit as x goes to infinity of 1 plus 1 over x to the x power. So that's where that comes from. All right, so here are a couple of properties that we need to know. And as I stated before, on the AP exam, there's tons of reference to the natural exponent e and the natural log ln on there. So y is equal e to the x if and only if x is equal to the natural log of y. Okay, the natural log and the natural exponent e are inverses of each other. E to the natural log of y is equal to y. And the natural log of e to the y is equal to y. Also recall that the natural log is just a log with a base of e. Also recall that e to the a times e to the b is e to the a plus b And e to the a divided by e to the b is e to the a minus b. So the same properties that we had for exponents, they work here as well. Okay. So now I'm going to take you back a little bit to Algebra 2 and pre-cal. With solving logs, natural logs, and solving exponentials. Okay. All right, so let's take a look at this example. All right, so we have 7 is equal to e to the x plus 1. What's e? I'm sorry, what's x? Okay, so how do we solve this? Come on, I know you guys took Algebra 2. Did you do logs in pre-calc? Should have done logs in pre-calc as well. So you had 2 years of logs. Take the natural log. Okay. So here, if we take the natural log of both sides, okay, so what does that do for us? What do you mean by get rid of the e? Well, because the reason the get rid of it part works is because natural log and e are inverses of each other, so they undo. So the natural log of e to the x plus 1 is x plus 1. So x is equal natural log of 7 minus 1. Okay, let's take a look at another example. How about natural log of 2x minus 3, and that's equal to 5. Okay, how would we solve this for x? What value of x makes this true? Come on, guys. We took Algebra 2. We took pre-cal. How would you solve this? Multiply by e? Because e times 5 would just give us 2.718 approximately times 5. I'm not sure how multiplying this side by e would help us. Let's go back to the properties, though. Okay, so here e to the natural log of y is equal to y. Natural log of e to the y is equal to y. So because they're inverses, the composition of these functions, they undo each other. Now what you guys did here for the first example was kind of the same thing. You did the composition. The reason you took the natural log of this is because you wanted to undo the e. So you applied its inverse operation. It didn't necessarily inverse out the 7 because natural log and 7 aren't inverses, but that's fine. That gives us a numerical value. So we needed to undo the e. On this second example here, what do you need to undo? Natural log. So you need to use its inverse operation to undo it. So it's not multiply by e. It's e to the, ln of 2x minus 3 equals e to the 5th power. Now, I've often talked about functions being one-to-one, so one of the reasons that you are able to do this is because both e and natural log are one-to-one functions. So now this undoes the natural log, and you're going to get 2x minus 3 is equal e to the 5th. And solving, you're going to get x is equal e to the 5th plus 3, and all of that will be divided by 2. Okay, when I taught Algebra 2, I always just taught my kids, my students, that a log is equal to an exponent. If you want to solve a log, write it as an exponent. If you want to solve an exponent, write it as a log. And let me tell you what I mean by that. Let me show you what I mean by that. Okay, so every exponent can be written as a log. Every log can be written as an exponent. Every exponent can be written as a log. Every log can be written as an exponent. I'll give you an example. 3 squared is equal to 9. Okay. I can rewrite this as the log of my base. So here my base is 3. So log base 3. A log is equal to an exponent. My exponent is 2, so I know my 2 goes here. A log equals the exponent, so that means my 9 goes here. Log base 3 of 9 is equal to 2. Every exponent can be written as a log. Every log can be written as an exponent. Let's say you had log base A of happy face is equal triangle. How would you write this as an exponent? A to the triangle is equal happy face. A log equals the exponent, so I know that the triangle is my exponent. Here's my base. My base is A. My base, my exponent, is going to equal to that. So with the problem that both problems that we just had, the first one was 7 is equal e to the x plus 1. Okay, so a log is equal to the exponent. My base is e. Log base e of 7 is equal to x plus 1. Well, log base e of 7 is just natural log of 7. So all I did was I rewrote my exponent as a log. Subtract 1 from both sides, x is ln 7 minus 1, which is what we got doing the composition. Our other example, natural log of 2x minus 3 is equal to 5. So to solve this one, I'm going to write my log as an exponent. Log is equal to the exponent. So my exponent is a 5. My base is e. E to the 5th is equal to x minus 3. Add 3, divide by 2. There's my answer. Okay. Okay. So whether you look at it my way as just to solve a log, write it as an exponent, to solve an exponent, write it as a log, or doing the actual compositions, is fine. You'll need to know how to do both. All right, any questions? Okay, so we're going to repeat a little something that we already learned, and that is that the derivative of e to the x is equal to e to the x. And the derivative with respect to x of e to the u is e to the u times u prime du dx. Now, we actually already proved this, right? Do we need to see the proof again in our notes? Why not? All right. It was not a long proof. The derivative of e to the 2x minus 1 Okay, Jelini, what is the derivative of e to the 2x minus 1? Well, the derivative of e to the u is e to the u times the derivative of u. So the derivative of e to the 2x minus 1, we know it's going to be e to the 2x minus 1. Now we just need the derivative of 2x minus 1, which is 2. Okay, that's it. Okay, now how about this one? Yes. Okay, this problem we saw on the Unit 4 test. You're going to see it again on the Unit 5 test. What's the derivative of e to the negative 3 over x? So 3 over x squared times e to the negative 3 over x. Or 3e to the negative 3 over x squared. So how did you get the 3 over x squared? Quotient rule? Can we rewrite negative 3 over x as negative 3x to the negative first power? Then the derivative will be negative 3 times negative 1, x to the negative 2. Negative 3 times negative 1 is a positive 3. X to the negative second is 1 over x squared, so you get 3 over x squared. I'm hoping at this point you guys are seeing kind of like the pattern when you have the constant over x. And then as you continue to take the derivatives, what's happening there. All right, so any questions there? All right, I am going to throw some Unit 3 in there for you. Some Unit 3. Okay, and I will give you the roughly 3 minutes that would be given to you on the AP exam for this problem. Find all local extrema for f of x is equal to x e to the x. All right, ladies and gentlemen, you have 3 minutes. Okay, about 45 seconds.
Factor out the EX.
Okay, are we ready? All right. Lorena, where do we start? Where do local extrema or relative extrema occur? Like how would we know if we had a relative max? What would have to take place for a relative max? What's changing? So the graph of f prime, so the derivative. The derivative of it would have to go from what to what in order to be a relative max? Had to go from what? The derivative? If the derivative goes from increasing to decreasing, that means that the second derivative goes from positive to negative. So what has to go from negative to positive? The graph of what? Huh? F prime. So the graph of f prime goes from negative to positive. Then that means your function is going from decreasing to increasing. So in that case, you would get a relative min. If f prime goes from positive to negative, then that means that if f prime is positive, your graph is increasing, f is increasing. If f prime is negative, then f is decreasing. So if f prime goes from positive to negative, then f is going from increasing to decreasing, and that's where you get a max. Okay. So in any event, we need to determine if f prime is changing signs. So my original question to you would be, where exactly would relative extrema occur? How would f prime go from positive to negative? It would have to be what first? Zero or not defined. So where your derivative is zero or not defined are possible relative extrema points. So first thing we need to do is take the derivative and set it equal to zero, or determine if it's not defined. Okay. So, Esmeralda, what's our derivative of f? Did you say something? I didn't hear you. So what's our derivative? So f of x is equal to x times e to the x. So what would our derivative be? What would f prime of x be? Go ahead and go up to the board, grab a marker, do it on the board. Sometimes it works a little better if you write. Go ahead and do it. So f prime of x is equal to what? So what? Did she use the product rule? Because she has two functions. She has f of x times g of x. So doesn't she have to use the product rule? Oh, okay. So what's the derivative using the product rule? The first times the derivative of the second plus the second times the derivative of the first? Okay. So first times the derivative of the second plus the second times the derivative of the first. Okay. Isn't that the derivative using the product rule?
Yeah.
All right, so now we need to determine where this is equal to 0. X is a continuous function everywhere. Each of the x is a continuous function everywhere, so we're not going to have a case where this function, where this derivative is not defined. So is this derivative equal to 0 anywhere? Well, this is the same thing as e to the x times x plus 1. And then we should know that e to the x is never equal to 0. The graph of e to the x does this. It's never negative, it's never equal to 0. So the only time this derivative is going to equal to 0 is when x plus 1 is equal to 0. All right, so your graph is equal to 0 when x is equal to negative 1. All right, so let's go ahead and choose a couple of test values. What would you like to choose? 0 and negative 2. Okay, f prime at negative 2. Let's see, here's f prime right here. So at negative 2, it doesn't matter what you put in here because e is always positive. So even if I put a negative 2 in here, e is still above the x-axis as positive. So I don't have to worry about the e to the x. It's always positive. So I'm just substituting my value of negative 2 in here. Negative 2 plus 1 is negative. When we evaluate at 0, e to the 0 is 1. 0 plus 1 is 1, so we're positive here. So at negative 1, f prime goes from negative to positive. So that means that f goes from decreasing to increasing. So do you get a relative min or a relative max there? Relative min. So you're going to get a relative min at x equal negative 1 since what? What's your justification on the AP exam? Since what? Since f prime changes from negative to positive at x equals negative 1. Okay, now what is our minimum value? So our relative min occurs at x equals negative 1. What's the value at negative 1? Where would you substitute that? Edward, where would you substitute that? To find the minimum value. We know our minimum occurs at negative 1. What is our minimum value? Substitute into f of x. So minimum occurs at f of negative 1, which is equal negative 1 times e to the negative first power, or negative 1 over e. So our minimum value is negative 1 over e. E to the x plus e to the negative x. What's du? E to the x, and the derivative of e to the negative x is negative e to the negative x dx. So here is your du. Du is equal e to the x minus e to the negative x times dx. So this now becomes the integral of 1 over u du, which is natural log absolute value of u plus c. And now we're going to back substitute. So that's the natural log of, and I don't need the absolute value anymore because e is always positive. So that's natural log of e to the x plus e to the negative x, and then plus c. All right, any questions? Okay, so these are the types of problems that you guys are going to be given. Super easy. All right, if you guys don't have any questions, you can go ahead and start on the assignment.